Well, let's assume you put together a design as shown on the screen, a design that has an IP that does stuff and also a neighborhood processor. Basically takes in pixel from an image, transfer them into a different image. And I'll get to this in a little bit. Let's say you've successfully synthesized and tested on hardware and it resulted in a whopping high utilization, 86% on LUTs. So you're about to close out the design lead comes in telling the team there has been a change in requirements in which we're going to have to increase the number of processing in neighborhood processor. So we're going to make this block much more powerful. This will take more space and require some resource. But looking at the resources utilization, you're underwater. How is this even going to be possible? A possible solution in which you're considering is moving on to a much larger FPGA. But before taking this drastic move, we decided to look into the code and see if there's areas in which it can be optimized. Well, that is a good start. This thing looks like it can be optimized. In a nutshell, this algorithm takes in pixel from an image and multiplies them by a bunch of kernel elements, and the result is added together to produce a new, much happier image. So the requirement presented by your design lead is to basically expand the processor to process more pixels. So how do we tackle this? Let's for a moment forget about the details on this algorithm and let's just pay attention to this block. We have multipliers, we have registers, and then we have a multiple input adder. And if we look at the details on how it's going to be implemented on an FPGA, I have a simplified block diagram of Xilinx FPGA here. Instead, it's going to go directly into any of these elements right here, but it will definitely omit these blocks right here called DSP blocks. And this is the key to our solution. We're going to be leveraging those DSP blocks to optimize the design. If we look at the resource utilization, you can see that none of the DSP blocks are used in this design. And now if we look back in our simplified block diagram and zoom in into one of these DSP elements, you will find these components. Ignore all the complexity and look at this. You have a register, a multiplier, a register, and an adder. Does this ring any bell? Let's go back to the algorithm structure. You have a register, you have a multiplier, you have a register, and finally an adder. Now stay with me here, guys. This is where the magic happens. If you look at this, we have a 2 input adder in the DSP element, and then we have a multiple input adder in our algorithm. And this is exactly what's preventing the tool from directly implementing this algorithm into one of those DSP elements. And even if you had a 3 input adder, your requirement is expanding this to a multiple input adder. And this is making this algorithm not compatible with the DSP element. And the fix to this problem is to restructure this into a way that it will have multiple 2 input adder. Now quickly returning to our implemented design, here's our limited multiple inputs adder wasting away DSP element. We are also illustrating how we expanding this to n input pixels. Now let's restructure this design in a way that we have multiple 2 input adder. Look at this new modified design. If you pay attention closely, the input is coming in serially, which before it was coming in parallel, and now we have a sequence, a chain of 2 input adders, and that allows us to go directly into the DSP elements. And now if you look at this design, it looks completely different, but stay with me here. So while the 2 designs are implemented using different techniques, they are functionally the same, meaning same input will give you same output on both structures. Now latency is different, but that's negligible. Another critical difference between these 2 designs is how they expand in the FPGA. While structure 1 expands using configurable logic elements, structure 2 introduces the DSP element of the FPGA. You can see how you could expand this algorithm to use more DSP blocks, freeing up combinational logic elements for other purposes. Well, the 2 designs were implemented for comparison. While Technique 2 was expanded to process 3 times more pixels than Technique 1. And the result is outstanding. We can see how Technique 2 expanded in the DSP domain, leaving TLBs untouched. While if the same number of processing were applied to Technique 1, we would have problems because of space limitation. And this proves the point of creating more efficient design if you know more. And of course, this is only applicable if space really matters to you. Thanks for watching. I hope this helped. Peace.